Machine learning is often sold as a magic wand that turns raw data into perfect decisions. The reality is far more brutal. When you move from simulation to the physical world, your algorithms face a wall of noise, latency, and hardware degradation that they were never designed to handle. This gap between the digital ideal and the analog mess is where autonomous systems fail. By the end of this analysis, you will understand why the most sophisticated models collapse under real-world conditions and what engineering principles actually bridge that divide. For decades, machine learning was treated as a purely mathematical discipline. Scholars like Janiesch defined it as automated analytical model building, while Yunes and Sin insisted on rigorous foundations in calculus, probability, and optimization. These theoretical frameworks work beautifully in a controlled environment where data is clean and perfect. You can train a neural network on a dataset where every pixel is labeled correctly and every sensor reading is instantaneous. In that world, the system learns to generalize with high precision. But this is a fantasy. The moment you deploy a model into a physical robot or an autonomous vehicle, the assumptions that made the math work begin to crumble. The first major point of failure is sensor noise. In a simulation, a camera sees a perfect edge. In the real world, a camera sees dust, rain, and changing light conditions. Machine learning models are incredibly sensitive to these perturbations. A small shift in pixel values that looks like random noise to a human can completely change the classification output of a deep learning algorithm. This is not a bug, it is a feature of how these models learn to find patterns. They latch on to the statistical regularities in the training data. When the real world introduces variations that were not present in the training set, the model does not just get slightly less accurate, it often becomes confidently wrong. This is the phenomenon known as adversarial vulnerability, where the system is robust to the expected but fragile to the unexpected. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Now consider the problem of latency. In a simulation, the loop between sensing, computing, and acting is instantaneous. You send a signal, and the result is immediate. In a physical system, you have to deal with the speed of light, the processing time of your hardware, and the communication delays of your network. An autonomous drone flying through a storm does not have infinite time to compute its next move. If your machine learning pipeline takes too long to process a sensor reading, the drone will have already moved past the point where that data was valid. The decision it makes is based on a snapshot of the world that no longer exists. This temporal mismatch creates a feedback loop of error that can spiral out of control faster than any human operator could react. There is also the issue of hardware degradation. A simulation assumes that your computer and your sensors will function perfectly forever. In reality, electronic components drift. A camera lens gets dirty, a motor loses torque, a battery voltage sags under load. These are slow, continuous changes that do not happen in a training dataset. A model trained on pristine hardware will struggle to adapt to a system that is slowly breaking down. The mathematical frameworks we use, such as the evidence lower bound, assume a static distribution of data. They do not account for a world that is constantly changing its own rules. When the hardware degrades, the distribution of the input data shifts. The model is now operating on a distribution it has never seen, and its performance degrades rapidly. This creates a significant knowledge gap in the current state of the field. While foundational texts prioritize statistical generalization and algorithmic design, they often ignore the messy reality of deployment. We see a divergence where academic papers focus on improving accuracy on static benchmarks, while industrial applications stress the need for robustness in dynamic environments. The result is a system that is theoretically sound but practically fragile. We have built massive industrial infrastructure with tools like LightGBM to drive efficiency in ranking and classification. Yet we have not solved the fundamental problem of how these systems behave when the physical world pushes back. Here is the thing that most engineers miss. The solution is not to build bigger models or train on more data. The solution lies in rethinking the relationship between the model and the hardware. We need to move beyond the idea of a static model and embrace systems that can adapt to their own degradation in real time. This requires integrating probabilistic data quality checks directly into the learning loop. Instead of assuming a sensor reading is perfect, the system must estimate the confidence of that reading based on the current state of the hardware. If the camera is dirty, the system should downweight the visual data and rely more on LiDAR or radar. This is not just error mitigation. It is a fundamental shift in how we design autonomous systems. The tension between rapid deployment and rigorous interpretability is becoming the defining challenge of our era. As we integrate these tools into healthcare, finance, and emotional processing, the cost of failure increases. We are seeing a rise in hallucinations, where models generate plausible but false information because the underlying architecture is not robust to the noise of the real world. We need new educational roadmaps that address not just how to train a model, but how to build a system that can survive when the training data no longer matches reality. This involves a deeper understanding of the socioeconomic context as well. The servitization of AI means that these systems are becoming embedded in our daily lives, and we need to ensure they are robust enough to handle the unpredictability of human interaction and environmental change. The path forward requires a synthesis of theoretical robustness and practical engineering. We must stop treating machine learning as a black box that produces perfect answers and start treating it as a component in a larger, imperfect system. This means designing for failure, building in redundancy, and creating models that can reason about their own uncertainty. It means acknowledging that the math of gradient descent is not enough. We need a new paradigm where the system knows when it does not know, and where it can adapt its behavior to match the current state of its hardware and environment. Only then can we move from theoretical foundations to complex, real-world applications that actually work when the lights go out. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.